All right here, folks. Can I have your attention, please? Excuse me. Thank you. Let's take a few moments here and take some questions from this assignment. So this is what I just walked by and checked. This was worksheet 2 from chapter 8. We're using our exponential models to answer some of these kind of story problem application sort of situations. Are there any of these that you guys want to talk about? Nancy? 5? Sure. So it says you deposit $10,500 into an account that pays 10.3% interest compounded daily. To write an exponential model where FV represents the value of the account after T years. So since this should be relatively obvious that it's a compound interest situation, that we're dealing with bank accounts and interest rates, we'll be using the compound interest formula. It says to use the future value just as FV. The present value should be the initial deposit, so 10,500. Our interest rate as a decimal, 0.103. And it says it's compounded daily. So how many days are there in a year? 365. So that's my value for N. That's assuming it's not a leap year. This year we had 366, but we'll assume no leap year here. Part B says asks what is the account's value after 7 years and 3 months. So remember, T is time in years. So I have to convert 7 years and 3 months into just a decimal for years. So how much of a year is 3 months? A fourth, right? Because how many months are there in a year? 12, and 3 is a quarter of 12. So for this, I'm going to use my time as 7.25. Is everybody okay with that? And we'll just type that in then. So what we have there was, darn it. Was about, okay, come on, about 22,154.04. And then for part C asks how long until the account is worth $1 million. So the way we're going to do this is we're going to do this by graphing. So, oops, got to change my mode out of that because I'm in a different class. Okay. So I'll start by writing my FV equation where Y is going to represent FV and T is going to, or X is going to represent T. So just like we've done before. And then my second equation is just going to be 1 million. And now I'm going to reset my window. So T is time in years. How long do I think it's going to take for this bank account to get to $1 million? I don't know. It feels like a long time. So maybe I'll go from 0 to 100, not really sure. And then the amount of money I need to get to is 1 million, so I want my Y max to be more than 1 million, so maybe I'll pick 1,500,000. Sound okay there? And again, the window doesn't matter so much. What a good window is just one where we can see the intersection. That's all we really need. So the window we chose here was good because we can find that intersection. You notice it took way less than 100 years to do it. That's fine. Usually I like to try to overestimate than underestimate because the last thing I want to do is have to change my window a bunch of times. So to find that intersection, I'm going to press second and the trace button, select the intersect command, and then I'm going to pick, the calculator asks for 2 questions. It asks first curve. So I'm just going to move my cursor just so I can make sure I can see where it's at. Going the wrong way. So there's my cursor. It is on one of the 2 curves I care about. I'll press enter. So it is on the straight line. That's one of the 2 curves I care about. And then it wants a guess. So just move it somewhere close. So it says it took about 44.2 years. Not too shabby to make $1 million in 40 years without having to do anything. All you had to do was sit there and wait. You know, it's the power of compound interest there. Although 10.3% return on any kind of investment is pretty bonkers. Anyways, do we feel okay on that, Nance? We're good? Any other questions from you guys? They were all kind of the same like this, right? So probably the trickiest part of that one was what to do with the 3 months. Cool. All right, so today, moving forward, continuing to talk about exponentials. So today we're going to talk about the exponential base. I'm sorry, that's not what I wanted to say. The natural base. So when we say the word base right here, I'm referring to the base of an exponential. So the base of an exponential is the number, the big number, right? So we have a base, and then attached to that base is like an exponent. Okay. So what I want to think back to here is this compound interest model that we talked about in the previous lesson. And I'm going to simplify this equation a little bit. And I'm going to let that present value be 1. And I'm going to let r equal 1. And actually, I meant to do one other here. I want t to be 1 here also. Excuse me. So what I want to look at here is I want to look at how does that future value change as FV changes? So the reason I want to do this is if we think back to what these different parameters mean, remember that n was the number of compounds per year, right? That was like the number of times that interest rate or that rate of change occurs, right? Let's think now about, say, like a natural situation, like a biological situation. Let's think about human beings, the population of human beings. Now, how many human beings are on the planet right now? 7 billion and change, right? A whole lot of them. How often do you think the population of human beings is changing? Probably more often than that even, right? So, yeah, like all the time. So from a mathematics standpoint, we would say like at every instant. Okay? So how many compounds per year would that represent? It's a what? Less than that. Less than that. So it's not a number. It's like just the smallest fraction of time that you can have. So the number of compounds per year then is infinite, right? If an instant is like an unmeasurably small sliver of time, that means you're going to have infinite of those compounds per year, right? And if you're dealing with any kind of large biologic system where the population is really big, the population is changing at every instant, basically, right? So this becomes a really important exponential base because we have lots of systems that things are changing at all the time, right? So specifically what we want to look at is what happens when n is going to infinity. Now, can I plug infinity in for this and get an actual result here and evaluate this out to a number? No. But what we can do is we can kind of do some test runs. So what I'm going to do is I'm going to just pick some values for n and then find the values for FV at some, order or some different orders of magnitude for n. So we'll start at 1, and then we'll do 10, and we'll do 100, and we'll do 1,000, and maybe we'll do a couple more, but this will be our start. Okay. So I'm going to have 1 plus 1 over 1 to the first. So when n is 1, we get 2. When n is 10, I get 2.59374246. And you don't have to write down all these decimal points here. We're just kind of doing a little bit of an exploration right now. So it's not like we're doing an example problem or anything. We're just kind of exploring this value right now, or this little situation. Now I'll put 100 in for n. So we have 2.704813.829. Okay. We'll do 1,000 now. What do you notice about how this value for FV is changing? So if I look at the difference between 1 and 10, it was like 0.59-ish, right? And the difference between 10 and 100 was like 0.11-ish. And the difference between 1,000 and 100 is like 0.01. What's happening here? Is FV growing faster or slower? Slower, right? In fact, it looks like it's eventually going to stop growing altogether. Does it kind of seem that way to you guys? No. Like that rate of growth, though, is continuing to slow down, right? You're right. It's not going to technically stop growing. But what's going to happen is that we say that it approaches some value. So let's do one more, and then we'll stop and define something here. Okay. So notice that at this point, going from 100 to 1,000, the first two decimal places have now been fixed, right? Those didn't change. As we go from 1,000 to 10,000, the first three decimal places didn't change, right? If we go from 10,000 to 100,000, the first four decimal places are now kind of fixed. They didn't change. We can keep making n larger and larger and larger, and we fix more and more of those decimal places at the beginning, right? So what we're going to do is we're going to define this rational number, because this decimal is just going to keep going. And you know how, like, in geometry, we defined pi, the number 3.1415, yada, yada, yada. We gave it a symbol to represent that because we didn't want to write this unending, never terminating decimal out. We're going to do the same thing to this number here. We're going to call this number E. We chose the letter E because the mathematician who developed this idea, his name was Leonard Euler. So his last name started with an E. That's why we've chosen the letter E here. Ty? So that's a different thing. So we'll talk about on the calculator. So the calculator, this E is not the same thing as this E. So this E is for scientific notation. Well, there's like a letter E if you're defining a variable in like a program. But no, these are the two E's that your calculator is using to do stuff. Now, there's two ways to get this letter E on your calculator. But I think that's the only e's that they're talking about. So if we go to Google and we look this up, and we look up the natural base E, and we look at, say, the Wikipedia entry on this, I'm betting they're going to give us some large approximation. No? I was really hoping for us to give me like 100 decimal places on here. Wikipedia, what are you good for? All right, well, I'm disappointed in the internet. I thought that was going to be easier than what it turned out to be. So, let's just do this. So, to get E on your calculator, there's two ways to get it. If I just want the number E, I can press second and the division sign. That'll give me the letter, that'll give me the value for E. Now, there's more decimal places than just what the calculator is representing. Just like on pi, there's more decimal points there than what the calculator represents. But this is just as much as it's going to hold. Matthias. Of course. Yes. But remember, it just keeps going, right? Also, just that's as much as your calculator will hold. The other place where you can get the value for E is if you press second and then the LN button that's located on the left-hand side. That'll give you the E, and it automatically puts like an exponent spot there for us. So if I want E to the first, that's going to be the same thing as just E. You notice I get the same value out of there. Okay with that? Okay. So what we can do now is this gives us two new exponential models. When are we going to use these two exponential models? In situations where the number of compounds is infinite, where things are growing like instantaneously. So those are situations that we'd want to use this in. So the first model I'm going to write is going to be FV is equal to PV times e to the RT. So again, by FV, we mean the future value. PV, we mean the present value. R, we want the rate of change as a decimal. E is just that number, 2.781, yada, yada, yada. And T is going to be time, typically in years, but it'll match whatever the rate is in the problem. So if your rate is, 7% each second, then time should be in seconds. If it's 22% every year, time would be in years. It just, the unit would match there. Everybody okay with this idea? So this is the model that we'll be using in these situations where things happen kind of instantaneously or continuously. The other situation that might occur is if we just give you the model inside of the problem and ask you to work with it. So I could do that also. There are some where I'll do that. But let's look at a couple of examples here of using this sort of situation. So the length L of a tiger shark can be modeled by the function L is equal to 337 minus 276 e to the negative 0.178 t, where L is in centimeters and T is the shark's age in years. So let's use this model then to estimate the length of this 3-year-old shark. Ty? Yes, go ahead. So we have this equation. What parameter are we looking for? Are we looking for the L or the T in part A? The L, right, because it's asking for the length. So to find L, we need to fill in a value for T. What value of T are we going to fill in? 3. So now I'll just go to my calculator and type this in exactly as it looks. So 337 minus 276 times e to the negative 0.178 times 3. So just typed it right into my calculator. How did I get the letter E there? I did second, and then the ln button, which is on the left-hand side of my calculator. That gives me the exponent automatically when I type that in. So I don't have to add the exponent in later. So when I do that, I get 175.2 centimeters. The next part of our question, I ask, how old is a shark that's 4 meters long? So again, we're going to use our model that was given to us in the problem. This time, which parameter am I looking for, L or T? T, because it's asking how old. Okay? So what am I going to plug in for L then to solve for T? Not 4, Well, 400. Why 400 instead of 4? Yeah, very good. So this is in 4 meters. We're told that L is in centimeters. So I had to convert 4 meters into centimeters. Okay. So just like we've done before, we'll solve this system using our calculator. So 330, clear that all out. 337 minus 276 e to the negative 0.178x, and then 400. Once we've got our equations typed in, we need to set a window. So in this case, our x is being represented by time. So this time is the age of the shark. So what's the least age a shark could have? 0. That'd be like a newborn shark. And how old do sharks get? Does anybody have a guess? I think they can get really old. I think they can get like 100 years old. I think they live basically as long as a person can.
It depends on the species.
Yeah, but like the big sharks, I think live for a long time.
Like there's sharks in Greenland that have been around for like 500 years.
Right.
And they've like lived through wars and stuff.
Yes.
And there's some like nurse sharks don't live very long. They only live like 30 years.
Right. Okay. But the point is, it's going to be a while, right?
Yeah,
a shark gets pretty old.
They don't. It's not like a man or like a.
Yes. Yes. So as far as an estimate goes, again, we'd rather overestimate than underestimate. I think 100 is probably big time overestimate, but we're safe there, right? Like we're going to definitely get enough. Everybody's okay with that idea? Okay. And now the y is representing the length of our shark. What's the least length a shark can have?
0.
That's like a shark that hasn't been born yet, 0 long. Okay. And then my upper for the length of a shark definitely needs to be bigger than what number?
0.
Well, definitely bigger than 0. Then what? 400. So let's pick like 500, right? That's bigger than 400. All I really need to be able to see is the intersection. A good window is just one where we can find the intersection. Uh-oh. What do we have going on here? Doesn't look like it's going to cross here, right? Why do you think that is? Did we do anything wrong?
Because it can't get smaller than 0, right?
What is it?
Shark.
The shark can't get smaller than 0. That's true.
Isn't it the HA? Is the line not supposed to touch the line?
Right. So the HA in this case would be like this 337 here, right?
Is that where the straight line is on the graph?
So the straight line is at 400, which is above 337. You know what happened? Mr. Kulik picked a bad number. So what this basically says is tiger sharks don't get 4 meters long.
Yeah, that's a pretty big.
That's a pretty big shark. I wasn't really thinking when I picked a number. I just wanted to pick something where we had to convert the units. Oops-a-daisy. So let's just make that 2 meters. Yeah. So if we do that, I think everything's going to work out. Yeep. So there we go. Right? We can see the intersection happens like right away. Which is not surprising because a 3-year-old shark we know is 175 centimeters.
Yeah.
So this is just a little bit going to be a little bit more than that.
Yeah.
So if I go to second and trace, pick the intersect command, first curve, second curve, and then scroll over to make my guess, the calculator is going to spit out my value here, which is 3.93 years. So in general, is this really any different than the previous homeworks questions? No, not really, right? Not really. Okay. Let's do another example here before we move on. Bless you. Okay. Let's say that we deposit $2,500 in an account that pays 5% annual interest compounded continuously. We want to find the account value after 5 years. What is the word in this story problem that needs to be like in flashing red when I read this? Continuously. Because what is continuously telling me? I need to use a different model than I would if it said annually or weekly or yearly or quarterly or whatever. I need to use this model. Is everybody okay with that idea? So that's the word you really need to look out for on these compound interest problems, is that continuously, because it tells you you need to use a different equation. Okay. So if I'm looking for the account balance in 5 years, what parameter am I looking for?
FV.
FV, very good. Okay. So I have to fill everything else in to get that. So what is PV?
25.
Good. 2,500 is PV. E is the number E. That's just like pi. It's just a symbol, not a variable. What is R going to be? Okay. 0.05, writing it as a decimal. And my value for T is 5. So 2,500 times second ln 0.05 times 5. And I get $3,210.06. Reminder that when we are dealing with a problem like this with monies, we're always going to round to the penny because that's the least amount of currency we have, so the rounding always is going to occur there at the penny. What do you guys think? Not too bad, I hope, right? Very similar to what we've been doing. Not a lot of difference. We just have this develop this really useful new number, E, that we can use to deal with these situations where we have like continuous change happening. Just to go back for one quick second to this shark problem, why do you suppose that we needed E if we're talking about describing the length of a shark? How many different lengths can a shark have? Really infinite, right? Even if the shark is between 2 and 3 meters, there's like an infinite number of measurements in between that, right? So it kind of hopefully makes sense that we're going to be using this, because how often is the shark growing? All the time, right? And now it might be like an imperceptible amount that might be difficult to physically measure, but it's really growing all the time. So again, just to try to reiterate that. Okay. We're going to start here also the next section. So this next section, we're going to start talking about the logarithm. But I'm going to have a little bit of a slow build before we get there. All right, so I'm going to ask something that's going to be very difficult. I need you to remember all the way back to first semester. And I want to talk about the definition of a function again. Do we remember what the definition for a function was?
Yes. No.
Okay.
Yeah.
Help us out. Let's see if we can get it together here.
It's like a function is when you have x values that only turn one y value.
Excellent. Yeah, that's pretty good. So it's a set of ordered pairs. Where every x pairs with exactly one y. Very good. Now we want to remember what was an inverse function. Do you remember talking about this? This one we spent less time with. So, inverse. When we say the word inverse, just in an English language sense, what does inverse kind of mean? Like the opposite, right? Yeah. So let's say, for example, our function is the set of ordered pairs 1, 2, 2, 3, and 3, 4. What would the inverse of this function be? 4, 3, 3, 2, 2, 1. Yes, very good. So all that happened was we swapped the locations of the x's and y's, right? Yes. So that's one way of thinking about an inverse, right? If we're dealing with functions that are just sets of ordered pairs, it's a really rather convenient way of thinking about an inverse. Now, what if we're dealing with a function that's represented with an equation? What would the inverse there look like? So we say that f and g are inverses if and only if f compose g of x is equal to g compose f of x, which is equal to x. So, for example, these two functions are inverses. Let's show you why. Okay? So the first thing we're going to do is f compose g. When I say f compose g like this, what do we really mean? It means I'm going to take the function g of x and plug it into the function f of x. So what I'm going to do is I'm going to take this function g, and wherever there was an x in f, I'm going to plug that in. Everybody's okay there? Notice that here I have a times 2 and a divides by 2, so those can cancel out. Oops. I thought I changed that color. And then I have a x minus 5, and then a plus 5 at the end. So those can cancel out. And I'm left with just x, which is what we needed according to our definition, right? Everybody's okay there? Okay. So how did I find this g of x? There must be some way to do it, because Mr. Kulik just made this problem up off the top of his head and was able to write down the inverse really without thinking about it. So there must be a way to do this that's not terribly complicated. So let's do that. So let's just take this inverse 2x plus 5. So what I like to do is I like to start by replacing that f of x with just a y. And what I'm going to do now is I'm going to solve for x. I'm going to get the x by itself. So to do that, I'll subtract 5 from both sides. And I know I can't subtract 5 from a variable, so I'll just write the minus 5 right next to it. And then I'll divide both sides by 2. And again, 2 doesn't go into a variable, so I'll just write divides by 2 underneath it, write it like a fraction. Now the x is by itself. The last step here is to swap the x and y variables. So everywhere there was a y, I'll write an x. And everywhere there was an x, I'll write a y. So this new function, instead of calling it y, I'll call it g of x. And that's kind of how we find these inverses. Okay with that idea? Yes?
I mean, I guess.
Okay, Nancy?
I kinda get it.
Okay, where do you feel fuzzy?
The inverse part.
So just me swapping the x and y?
So what numbers did you start off with?
So this was the function that we wanted to find the inverse for.
Oh. Okay. That's just y.
So I just rewrote f of x as y. And then when I got the y back by itself at the end, I just replaced it with a different function name. I called it g because this is not the same as what f was, right?
Okay. I do.
Okay with that? Okay. All right. So why did we do all of this here? Because this is how we're going to define a logarithm. You may.